Hi, guys. Welcome to today's lesson. We're still working in chapter 6. Before we start, I just want to say I really miss seeing you guys at school. And this is just not the same trying to do this all from a computer. But I look forward to seeing you all in school next year. And I also want to say that I really appreciate the work you guys are doing because you're doing a great job staying up to date with the work, and the quality of your work has really been impressive. I'm not surprised because you guys are a great bunch. But I still want to thank you for doing everything you're doing. So let's go ahead and let's talk about chapter 6. In chapter 6, we're getting to the end of it, but we have to do some applications. That's code for word problems. So we're going to spend a couple days doing applications or word problems, and then we'll do a little review, and then we'll have some sort of chapter assessment. But don't stress about the chapter assessment. It will still be open note. It's not going to be even close to 100 points. I'm not sure how many points it'll be yet, maybe 30, 40 at most. All right. But just to kind of let you know where we're headed. So you're going to need a graphing calculator for today's lesson. So if you don't have your own, make sure you log on to the NJSLA website or the PARCC website and access that one on the website. So we're going to do 3 problems in today's lesson. So here's our first one. I borrowed this from the textbook, but I changed it up a little bit. We have this function here, and that's in this chapter because it's an exponential function. See how we have the number e there? That's not a variable. That's the special number e. That's called the natural base. It's about 2.718, but it's an irrational number. And there's a variable in the exponent. So this is an exponential function, and it models the population of a city where t is the number of years since 2000. So t equals 0 would be 2000. If you want to look at the population in the year 2010, you'd use t equals 10. If you wanted to look at the population in 2025, you'd use the year 25 because t is the number of years since the year 2000. So it kind of works like that. So what we're going to do first is use a graphing calculator to view this model from 2000 to 2060. So what you want to do in your calculator is you want to go into y equals, and you want to put in this equation. So it's 250, 3 more zeros. Be careful with those zeros. It's really easy to put the wrong number of zeros there. And then times e, you can do second ln, that's to the left of 4, to get e to a power. So second ln, or you can do second divide. Okay. And then once you have the e, you want to put your exponent of 0.013. And then even though this has a t, we're going to use x in our calculator because we don't have choice in variables here. X has to be our input and y has to be our output. So that's what we want to graph. You might notice I have another graph down here. That's for later. And that won't be in my way because you see how this equal sign is darkened? That's the only one the calculator is going to graph. See down here, I've stored this equation for later use, but the equal sign is not darkened, so it's deselected. So if I wanted to graph both, I could turn that on, but I don't want to graph both right now. And that's kind of handy to be aware of because if you're ever doing work and you might want to go back to an equation, like if you're taking a test in class, or if you're doing homework and you want me to see the equation you put in the calculator the next day. You can keep the equation there without having the calculator graph it. So it's all about having that equal sign on or off. Okay, so we're going to graph this. Let's start in Zoom Standard. That's Zoom 6. And when you're in Zoom Standard, your window is set to have an X max of 10, a Y max of 10, an X min of negative 10, and a Y min of negative 10. And what we need to do is adjust the window. We are told that we want to see from the year 2000 to 2060. So that actually gives us our X min and X max because the time is the X value. The X value is the time and the population is the Y value. So what we want to do is go into our window and see from 0 to 60, because that'll take us when t equals 0, that's 2000. And when t equals 60, that's the year 2060. So this tells us our x min and this tells us our x max. Now go ahead and hit graph, and it's quite possible we won't see any graph at all. That happens often in these word problems because the numbers sometimes are too big. See, we only go up to 10 right now because that's the y max that I have. We need to go up higher because the population, I'm going to guess the city has more than 10 people in it. So here's a tip for you. Hit trace. That is up on the top right here. Hit trace. Trace, when you hit trace, the calculator will tell you the point in the middle of the graph. So see how it says 30? So if this is 0 and 60, 30 is in the middle. And when x equals 30 or t equals 30, the population is 369,245, 369,245. That's why we can't see the graph. We're only going up to 10, and the population right in the middle is 370,000 people. So we need to increase that y max by a lot. You can make your y max 370,000, but chances are that's not going to be big enough because that's only the point that's right in the middle of the graph. So if you were to try that first, I think you'd say, this isn't the best window. We can do better. We can see more if we go up higher. So there's no set method for finding the appropriate y max. You try one. If it's not high enough, you try another one. If you go too high, you can always bring it back down. So let's try 450,000. Be careful with all those zeros. That's 450,000. That looks better, but I think we should go higher. I'm going to go 600,000. So I have 600 and 3 more zeros. And that looks pretty good to me. This is an exponential function. Remember what your exponential functions look like. They look like this. Okay, an exponential growth function. But we're not looking at this part because that would be negative time. So what we're seeing is just this part here. And if you're looking at this thinking it doesn't really look very exponential, let me adjust the window for a minute. Don't change yours. I'm not even going to show you what I'm changing it to because I don't want you to change yours. Just keep it the way it is. And let's see if I can give it more of a curve for you. Well, that didn't work. That's why. And maybe that looks a little more exponential to you. Let's see. Let me change it one more time. How's that? So I just changed the window so you could see that it really is an exponential graph. It's still that graph, but I made it like a really different window so that you could see that exponential growth. But the window that we're going to use, see, I actually had to go out to 1,000. That would be 1,000 years from 2000. That would be the year 3000. I think that's more than we need. So let's go back to just 2000 to 2060. And I think we had settled on 600,000 for our y max. Okay. And now we can go ahead and answer some questions. So here's that window again in case you need it. And the first question we want to answer is, according to the model, what will the population be in 2023? Round to the nearest whole number. All right. So for the population, are we looking for an x value or a y value if we want the population? We want the y value because the x value or t is time and the y value or p in this particular equation is the population. So the output's the population, the input is the time. So we want to know what will the population be in 2023. So what we want to do is plug 23 in for t. So there's a quick way to do that on the calculator. And that one way is to hit trace and then plug in, hit 23. And the calculator is going to plug in 23 for you and hit enter. So it's trace, hit 23, hit enter. And that's your population when the time is 23, when 23 years have passed and the year is 2023. So it's 337,127.41. It says to round to the nearest whole number. That should make sense because we're talking people. We don't want 0.41. in our calculations here if we're talking number of people. So we're just going to round that down, and we get 337,127. And I'll put people because we're talking about the population of a city. And then for our next one, we want to know how many years it will take for the population to reach 425,000. So this time we're given the output. This is our P or our Y value, and our job is to find T, or in this case for our calculator, the X value. So I have a favorite way to do that. If you want to find when we hit a particular Y value, my favorite way to do that, because it's really efficient, is to go into the calculator and graph Y equals whatever that value is. So in this case, it's Y equals 425,000. Make sure you get 3 zeros on there. And that's going to graph a horizontal line at 425,000. And if we find that point right there, we'll know exactly when the population hits 425,000. So do second trace intersect. The calculator will put you on your first graph. So that's Y1 for me, which is the exponential. See, it says first curve and it's on Y1. So go over as close as you can to the point of intersection, hit enter. The calculator puts you on Y2 and it says second curve. So if I were to go left and right now, the calculator would follow that horizontal line. But I want to get close to the point of intersection, and I think I'm already there. So I'm just going to hit enter. And then it says take your guess. I think we're already there. So I'm going to hit enter again. And you'll know you're finished with the process when it says intersection. So here we have it. When it's been 40.81, so 40.82 if we round to 2 decimal places. 40.82 years, the population will be 425,000. So if you want to write that down again, if you have the Y value and you want to find when that happens, put a horizontal line at that Y value and you can find the point of intersection. So for part C here, the year is 40.82 if we round to 2 decimal places. And that's how many years it takes before the population reaches $425,000 according to this model. And it says how many years will it take? So this is a good way to put that. If it said in what year, I would say it happens in 2040. So it doesn't word it that way in this particular problem, but if it said in what year will the population reach 425,000, then in the year 2040 would make more sense. All right. Let's continue. Let's go down to number 2. So this problem I took from the extra practice section of our Pearson resources, and I modified it, changed it up a little bit. So we have a hurricane center uses this log function. That's common log base 10, because it doesn't have a base written. And it relates the wind speed in miles per hour. So S is the wind speed, and D is the distance the hurricane travels. So the S is for wind speed, and D is distance the hurricane has traveled. And the distance is miles and the speed is miles per hour. So what we want to do first, according to the instructions, is graph the calculator from 0 to 20. So I'm going to turn this off and turn this one off because maybe I want those later. So I'm going to leave those there and just deselect them. You can clear them out if you want and just put this as Y1, but I just wanted to show you that you can actually store these in case you want to refer back to them later. So go ahead and put 95 log of X. Again, we don't have a choice in variable here. We have to use Y for the output and X for the input. And close the parentheses, then put 75. Let's start in Zoom Standard. Hit Zoom, please. Go to Zoom 6, which is Zoom Standard. And then it tells us what to use as our X min, X max. So for my window, I'm going to go 0 to 20. And when I hit graph, I might not see anything. I'm not sure yet. Yeah, a lot of times these numbers don't fit in here. So the trick from last time, do you remember what button I pressed? I hit trace. If you hit trace, the calculator will give you whatever points in the middle. So since this is 0 and this is 20, it tells me that at 10, I'm up at 170. That's why we can't see the graph. So let's change our Y max. We need to go up to at least 170. So you pick here, you can try 170. I'd probably go higher. I'd go 200, maybe 250, maybe 180. There's no exact perfect pick right now. So I'm going to go 200 and hope that's good. And if not, I'll just change it again. No big deal. It's pretty good. Maybe you want to go up a little higher to have a little more space there. So maybe go up to 220. But I think 200 works fine. If you were at 190, you're probably fine. And this is a log graph. Do you remember our log graphs? They look like this. So this is some variation on our log graph. I think you can see that shape here. So this is a pretty good window for us, and we have two jobs to do. We want to know the wind speed when the hurricane travels 2.6 miles. So remember, for our table, X is our input, Y is our output. We're using D, so distance is being treated as the input or the X value here. And Y, the output, Y is being treated as S, and that's the wind speed. So for part B, it says, what is the wind speed when we travel 2.6 miles? So is the 2.6 D or S? The 2.6 is D because we're looking for wind speed. The hurricane has traveled 2.6 miles. So this is your D value or your X value, and we want to find the Y. So a quick way to do that is to hit trace. You know what? Let me just write down one more thing here. So for the X-axis and Y-axis, this is the distance, D in miles, and this is the wind speed, S in miles per hour. And maybe that helps because it can be hard to keep track of which variable represents the input or the output, which one's the X value, which one's the Y value. Okay, so 2.6 miles is the X, so we want to plug in 2.6 and find the Y that goes with it. So to do that, we can hit trace, and then 2.6, and then hit enter. And what I get is 114.42, and it says to round to 2 decimal places. So we'll put 114.42, and don't forget to put the units on there. Since this is the wind speed, in this problem, that's in miles per hour. Wind speed is not always in miles per hour. It could be kilometers per hour, it could be meters per second, it could be feet per minute. But for this problem, it said in the problem itself that we're dealing with miles per hour for the wind speed. And then for C, we want to know how many miles a hurricane with this wind speed will travel. So this is our S value, that's our output. So what we're looking for here is when do we hit 135 on the Y-axis? So to figure that out, if we put in that horizontal line on the graph, we can then find the X value that goes with it. Okay. So we're looking for when we have a wind speed of 135. So I'm going to graph that along with my log graph. And this is the X value I want to find. So second trace intersect. And first curve, second curve, and guess. And I have 4.28, right around 4.28 to get a wind speed of 135. And this was S or D? This was D. So distance was measured in miles. So if the hurricane travels 4.28 miles, this would be the wind speed according to this particular model. So a couple things again, just to reiterate, just to repeat. You want to keep track of which is your input and which is your output, because in the calculator, you're going to be using X and Y, but in your word problem, you might have different letters. I think this graph may have really helped for this one. For population, on the previous example, you might not have needed it, but I think for this one, it was a little harder for me to keep track of which was D and which was S. You also might want to write down that the distance is in miles. I know we said it a couple times, but if it helps to write that down, it's a good idea. And the wind speed was in miles per hour on this one. So if you're given an X value, just hit trace and plug in that number, hit enter. If you're given a Y value, graph that horizontal line and find the point of intersection. All right, one more problem to do here. And the next one is actually, we could solve it by graphing, but we're going to just solve this one using the calculator's home screen. So the home screen, by the way, is when you're not in the graph. So just the regular screen. So if you're in the graph right now, hit second mode. If you hit second mode, that will take you to the home screen where you do all your operations. So this one I took from the textbook as well and changed it up a little bit. So in this particular problem, Miguel is collecting data on the number of people that go to an amusement park. And he figured out that based on the daily high temperature, this right here, which involves common log again, can actually approximate the attendance in thousands of people based on the high temperature for the day. So here is a little something from our weather app. That is not what we're looking at for next week. I think it might be a little colder next week, and I think it's supposed to rain like all week. Hopefully that'll change. But what we want to do is use this information to find the expected attendance on Wednesday. We totally could graph this. There's nothing wrong with that, but I'm going to skip that because we don't have to. We don't always have to graph to solve. Let's look at what we have and see what else we can do. So we have an equation here that's a equals 2 log of t plus log of 5. And this is the attendance in thousands. And T is the high temperature for the day in degrees Fahrenheit. So if we're interested in the expected attendance on Wednesday, we want to look at Wednesday. The low is 61, the high is 65. So 65 is what we want to use. And all we need to do is plug 65 in here. And again, you totally could graph this and solve it that way. But I think if you look at what we have, it's pretty quick just to plug in. Hit 2, hit log, that's common log. Since no base is written, it's base 10. 65. Make sure you close those parentheses before you add log of 5. And what I get here is 4.324796,718. The calculator has rounded that, but I'm going to go ahead and write all the decimals, and you'll see why in a minute. This is rounded, okay? But let me write that down first. And we want to give our answer to the nearest person. So what is the answer here? It's not 4. Okay, it's not 4 people. Think about that for an amusement park. That's not a good level of attendance. Remember that this was in thousands of people. So what you want to do with this number is you want to move that decimal point 3 places. If it were in tens, you move it 1. If it's hundreds, you move it 2. If it's thousands, you move it 3 places. So 4324.796718. So this is in thousands. And if we slide that decimal point 3 places, here's how many people we get. 4325. So it's a little tricky on this one because you don't want to round here because you'll think you'll have 4 people, or you might just think if you round to the whole number there, you might think you have 4,000 people. But we can be more precise by kind of using this and then just sliding the decimal 3 points. So 4,225 people is the expected attendance at the amusement park on that day. And once again, you totally could graph this. If you wanted to graph that, you would just have to find an appropriate window, and then you can plug in the X value. You'll get that same answer. So just to show you, you could do that. So if you wanted to graph this function, you would use X instead of T. Don't forget to close the parentheses, and then you'd have to find a window. That's kind of the time-consuming part. I decided my window would go from 40 to 90, because that represents temperature. So I don't think anyone's going to the theme park, the amusement park, if it's below 40. Maybe I should go up to 100. I think sometimes people will go even if it's really hot out. Okay, so there's my temperature range. And then this is in thousands of people. So I don't think there's going to be more than 10,000. So you'd have to find that window on your own, which is why I don't think it's worth it. I think you're better off just plugging in the home screen. And then if you hit trace, the high temperature was 65. And there's our 4.325, which will be 4,325 people. Thanks for watching.